Good afternoon, everyone, and welcome to the lecture number 6 of our course on quantum computing. So today we're gonna finalize our discussion of the basics of quantum mechanics, specifically for quantum computing in the way we formulate it. So namely, we will discuss the last two postulates. We're also gonna touch upon these very important concepts of pure and mixed states, and also the concept of uh, density matrix and density operator. But before we start the material of today's lecture, let me quickly go through the material of the previous lecture. Right, so in the previous lecture, we discussed the postulates from number 3 to postulate number, I guess, 8. Postulate number 8. So the postulate number 3 basically says that any physical observables or the quantities that we measure in a lab must be represented by Hermitian operators in quantum mechanics. Because only Hermitian operators can have real valued eigenvalues. And since the quantities we measure in the lab are real values, so they must be represented by Hermitian operators. The postulate number 4 says that when we measure a system that can exist in a superposition of basis states, basis vector like this, in the result of this measurement, we get only one eigenvalue from the series. And when we get this eigenvalue, the system collapses from the superposition to one of these basis states, only one state. And this is known as the postulate of collapse of wave function. So this process can be represented by these projectors or projection operators formulated in this way. So today we're gonna use this formula somewhat. So the next postulate tells us, well, basically, it formulates a way how to calculate or measure the expectation value for a system. So let's say, again, your quantum system can be given in a superposition of different states, and you measure like energy, and the first measurement gives you like energy 1, another measurement gives you energy 2, the third measurement probably gives you once again energy 1, and so on. So you get this result in a probabilistic way, and this formula tells us how to calculate the expectation value if you know the operator of the value we measure and the state, this general state of our quantum system. We discussed a few nuances. Let me skip all this. And repeat the postulate number 6, which tells us that only observables whose operators commute can be measured in the same experiment. So in order to define whether the observables measurable simultaneously or not, we introduce this concept of a commutator represented by this formula. So if commutator is 0, we can measure the observables A and B. If it's not 0, some value or some operator, then these observables cannot be measured with 100% certainty in the same experiment. Then I introduced you this library SymPy Quantum, which is very useful for symbolic quantum calculations. We discussed how to introduce a qubit and how to take the dagger of the qubit. We also say that these qubits or operators can be returned in their actual matrix form using this represent function operation. Yeah, we introduce the operators. We can specify that operator is Hermitian or operator is unitary by saying Hermitian operator, unitary operator. And then all the symbolic algebra with operators can be done using SymPy Quantum. Me personally, I use this library quite extensively because it helps with the calculations like this. And in particular, we can calculate the commutator of several operators and and do all the algebra. So finally, not finally, the postulate number 7 is about spin. So we postulate the existence of a spin as one example of internal degree of freedom of a quantum system that doesn't have a classical analogy, right? So it's not classic, it's a purely quantum effect, the spin. And interesting feature of the spin is that it can be observed only in spin up or spin down uh, uh, orientation. In this famous experiment, Stern-Gerlach experiment we discussed last time. And we introduced the concept of Pauli matrices. Again, today we're gonna use these matrices because they present some important quantum gates. Yeah, and using this SymPy quantum, it's very easy to work with these Pauli matrices again in symbolic form. Very important point about spin is that uh, it spin represented by three uh, operators, sigma x, sigma y, sigma z, along in corresponding to the number of different orthogonal directions in a three-dimensional space, and they represent the result of the measurements of the spin in the Stern-Gerlach experiment. And these Pauli matrices, of course, they are 2 by 2 matrices, and they have two eigenstates and two eigenvalues. So the eigenvalues are all the same because this is basically the result of measuring the spin. It can be along x or along minus x, along y, along minus y, and the same for z. However, the eigenstates are different. Eigenvalues are the same, eigenstates are different. And as we will see, this today, these eigenstates, they represent a very important states of a qubit on a Bloch sphere. So these all 6 vectors are well, they are orthogonal on a Bloch sphere, and yeah, and so they are very important for the future discussions. And finally, the postulate number 8 we discussed last time is about time evolution of a quantum system. So it's governed by so-called Schrödinger equation, the most important equation in quantum mechanics and quantum computing. And yeah, so we discussed some examples of the quantum of the Schrödinger equation. One important case is this stationary state when we just observe the behavior of a quantum system uh, without affecting it. So the system is in the uh, stationary state. All right. So we discussed that in this case, the Schrödinger equation can be solved by dividing the arguments, right? So in this case, the general solution for the Schrödinger equation can be represented as a product of two functions. One is purely spatial, another one is purely temporal. Okay, and the solution to the temporal one is the monochromatic wave, e to the power of minus I energy time t over h bar. So it's a monochromatic or basically sinusoidal oscillatory type of solution. And as a result, the total solution for the stationary Schrödinger equation is given by this formula here, where this special part of the wave function depends on the actual form of the Hamiltonian, basically operator of energy, Hamiltonian here. And as an example of the stationary Schrödinger equation, particularly simple to solve and at the same time quite important, is this case of a particle in infinitely deep potential well. Okay, so we assume that we have an energy potential distribution like this. So it's basically a well with zero energy, potential energy between two walls at 0 and A. Okay, otherwise the potential is infinite. So the particle cannot go to the left here and to the right here. So the particle is trapped between two walls in this deep potential well. Okay, so solution of this system, this problem is very simple because we simply imply that the potential energy here is 0. So the Schrödinger equation is simplified. So this is the Schrödinger equation in the stationary state. Right, with the Hamiltonian like this, with the kinetic operator and potential operator. And in this case, between the walls here, the energy is 0. So we omit this term, it vanishes. And we come to this simple equation, which can be solved by this ansatz, right? This gas solution. So we search for the solution as a sum of sine and cosine function with different amplitudes. Okay, so we substitute this solution to the Schrödinger equation and get this one for the this formula that connects the k, which is wave number, and energy here, right? Then we apply the boundary conditions. So I go a little bit in more detail here because we didn't have time to discuss this point last time. So I kind of go a little bit too detailed. So the boundary conditions apply that, I mean, since the particle cannot go to the left and to the right because the barriers are infinite, we must assume that we must take into account that the wave function at the boundaries turn into zero, right? So it's written here. We assume that at zero coordinate, this expression vanishes, so the coefficient b is equal to zero. Right, so we omit this cosine solution. Also, in the coordinate a, when x is equal to a, we get this expression here, and it also must turn to zero, again, because of the boundary conditions. And this solution gives us the following numbers, the following solutions for the k number. Okay, so now we see that the k number is not any number. In fact, it is quantized because of this n number here. So n here is integer number 1, 2, 3, and so on. Okay, and accordingly, the energy, since energy is connected to the wave number, accordingly, the energy is also quantized. So from this formula, you can you can obtain the formula for the energy here, and substituting for the k number, this expression, you obtain this formula here. So the energy of this particle in the quantum in the deep potential well, is quantized. And you can calculate any energy level of the particle in this well according to this formula. You can notice that there is the smallest amount of energy that the particle can have. This is the energy of the first energy level in this well. And the energy scales as n to the power of 2 quadratically with the number of the energy level. Okay. And of course, the solution for the wave equation, for the quantum state of the particle is given by these sinusoidal functions. So very important point to notice here is that applying the boundary conditions, so like trapping a particle, a quantum system in some dimension, in some area, leads to creation of a quantum spectrum. The energy becomes quantized. And not only energy, the other coefficients, quantities like wave number, also quantized. So when we restrict something, when we restrict quantum system, its spectrum becomes quantized. And in fact, if you consider other systems, for example, atoms, like simplest hydrogen atom, in hydrogen atom, the electron also confined, bound within its nuclei, right? So it moves in a certain finite area around the nuclei. And for that reason, the spectrum becomes quantized. So quantization is a result of trapping a quantum system, quantum particle in a well. So this is what we discussed last time, and let us transit now to the lecture number 6. And today we're gonna finalize this introduction to the basics of quantum mechanics, and we'll discuss some aspects of pure and mixed states and dephasing and an entanglement. Okay, so since this lecture, I'm gonna also upload these links to the YouTube video files that I recorded last semester when I basically taught the course using my tablet, writing the formulas. So I believe those video files actually very useful or might be useful, especially if I'll go for some aspects like too fast, right? So you can always return to these video files and watch them where I discuss maybe these things a little bit more detailed and writing formulas. All right, so as usual, we import some of these important general libraries first. I'm not sure I'm gonna use them much today. I mean, in this lecture number 6. I will use more these simple quantum libraries we discussed last week, so I import them too. And as usual, activate multiple outputs in my Jupyter Notebook project. Okay, so we transit to the postulate number 9. And the postulate number 9, as I formulated, says that the mixed states, so you hear this concept for the first time now, and I'm gonna discuss what I mean by a mixed state in what follows. But let us formulate this first like this. So the mixed state is described by density operator, also known as density matrix. Okay, so what is a mixed state? The mixed state is a state that so why we need mixed states? Okay, let me come to this point from this angle. So far, when we've been discussing these quantum systems models, we start from formulation of a wave function or the quantum state psi. Right? We usually say that suppose we have a quantum system in a quantum state psi. This quantum state psi, of course, can be a superposition of other states, and we call them basis states, right? We discussed that we can represent any quantum state in using this expression here. However, there is a large class of quantum systems that cannot be represented in this way. Okay, so we call this state as a pure state. However, a large class of quantum systems cannot be represented by using this formula, this state. In fact, a system like a quantum computer cannot be represented by this expression here. So, and when a system cannot be represented by this expression, we say that the system is in the mixed state. It's a mixed state. So mixed means that there is a mixture of something, right? So in this case, we mean a mixture of states like this. So when we need mixed states, here I put together two basically classes or two different scenarios when we need the concept of a mixed state. So one example is a classical ensemble of quantum systems. So let's suppose you have an atom, right? As we discussed, an atom can be described by the expression like this. For example, the hydrogen atom can be given by this s orbital state, then p orbital state, and so on, d orbital state. So this is a representation of a one single hydrogen atom. Okay. However, what if we need to describe a system of hydrogen atoms, like hydrogen gas, an ensemble of atoms? And of course, different atoms in such an ensemble, in such a gas, they can move with different velocities. They can have like rotations in different directions, and so on. So there is a classical uncertainty about the atoms that we don't know, and hence, and still this classical uncertainty affects our results. Okay, so our atoms not identical. Our atoms have a classical probability distribution. For example, over velocities. So here I bring some examples. So one example is Boltzmann distribution over energies, right? We know that a gas of atoms, it obeys the Boltzmann distribution of the energies for the gas as a whole, and different molecules in the gas can have different this classical energy in addition to the energy spectrum of each molecule itself. Okay. Another example is Maxwell distribution for velocities. Molecules can move, or they actually move with different velocities. And the probability that one particular molecule in a gas, or some number of molecules, will have a velocity, a particular velocity, or velocity less than a certain value, is given by Maxwell distribution. Okay, so this is the first example when we need mixed states. So the quantum state of this gas, the ensemble of molecules, atoms, cannot be represented by only this pure state. We need something else. We need to bring this mixed state description. Another example, and more relevant to quantum computing, is when a system is a part of a bigger system. Okay, like a quantum computer. Our quantum computer as a whole, of course, it interacts with the rest of the world, with the rest of the universe, right? And that interaction makes a quantum computer to be in the mixed state, not the pure state. Because when we focus on the description of the quantum computer itself, we kind of omit the details of the interaction of the quantum computer with the rest of the world. In this case, we say that the quantum system is embedded in a buff, like an external buff of other maybe quantum states, but we focus on description of this sub-state, which is a state, a part of a larger system. Okay, so I encourage you to read what I wrote here. The point, the bottom line is that the vast majority of quantum system cannot be represented in a pure state, and we need the mixed state description, and the description of the mixed state is conducted using density operator or density matrix. So having said all this, let me introduce the concept of density operator, which is quite general. Okay, and we have to start with the definition for the observable of an operator A. So in the lecture number 5, we basically discussed these observables here in the postulate number 5. Okay, so this formula is from postulate number 5 of the previous lecture. So this formula works for any case, for any system. And in a poor state, we always assume that the system can be in a superposition of basis states. Okay, so like we can represent this psi state using this series representation here, with n vectors being the eigenstates of some operator, basically basis in which we describe our quantum system. However, assume that now we have not one quantum system, but an ensemble of, let's say, identical quantum systems, like a gas of atoms, for example. So let's say we measure this observable in some experiment, okay? And we measure this observable n times. Let's say that we observe the one quantum system in a state n small 1 times. Okay, so we measure the system, for example, its energy or energy of a particular molecule. Okay, and we find that particular molecule, particular atom, n1 times in the state psi1, which is, for example, a state with some particular energy. And we observed this psi2 state n2 times, and so on. Psi n, n times, whatever. So from this experiment, we can introduce a classical probability, which is defined by like this, right? The number of times this we observe the state psi1 over the total number of the measurements of the experiments. Okay, so this number, this ratio, will give us the classical probability of finding psi1 state. Likewise, n2 over n will be the probability of finding the psi2 state, and so on. And now, if I sum up all these contributions together, taking into account the probability, which I denote by p with index I, right? We will get this formula here for the actual observable, the actual expectation value of observable A. So now this formula takes into account not only quantum probability, which is like encoded in the psi vector. Right? Psi vector, I remind you, each psi vector is a combination of basis vectors, and these basis vectors can be observed with some quantum probability defined by the absolute value squared of this coefficient Cn. Right? So this formula includes quantum probability. However, it also includes the classical probability given by this pi here. Okay, so both classical probability and quantum probability. Usually, we say that quantum probability is the like probability provided by nature, so it's not avoidable probability. Any quantum system works in a way that we cannot predict with 100% certainty what kind of result of experiment we will get. Right, like when we measure a spin, we cannot predict in which direction it will be oriented. So it's a kind of probability, it's a fundamental probability, not avoidable probability. However, the classical probability, which is given by this coefficient p with index I, so it's a classical probability. The classical probability comes from the fact that we don't know something about the system. Okay, so for example, if I know just two parts, like just two atoms in my system, I can measure the velocities or the energies of the entire system, of the molecules, the atoms. So I can know everything about the system. And in this case, I can return to the description by the pure state representation. If I know everything about my system in a classical statistics manner, right? Or however, if the number of quantum sub systems, particles, qubits is a large in my system, then I simply cannot gain all the information from the system that is necessary to describe it in a pure state. That motivates me to use a mixed state approach. So this is a mixture, hence mixed state representation. So now let us rewrite this formula a little bit by introducing the identity transformation. Okay, so this identity transformation, we have seen this one already. So this transformation is basically fair for any orthonormal basis vectors n. Okay, so for any set of basis vectors n, we can always compose this outer product of each vector, sum up, and it will give us the identity operator. Yeah, so using this identity transformation, we can insert this this expression, because since this identity doesn't change anything, right? So I write this formula here and insert this identity transformation between the, oops, I probably forgot operator A here. Let's see where it is. Now it's the identity. So, so I guess I need to write here, yeah. So this operator A here. So I just introduced this identity transformation between the operator and the state psi here, right? So this is the identity transformation. So I can take this summation sign out of from this expression and put it in front here, right? And this is what I have left. So this is rho. It should be. Sorry, it should be. I don't know why it's rho. Piece of I. Piece of I. Yes. So next, this is of course some complex number. This is another complex number. We can exchange the order of writing them. And I put this highlighted one first here, okay? On the other hand, now I can notice this expression encapsulated between two basis states n, here and here, right? So I can take this, take into account that the classical probabilities are real valued numbers, so constants. I can insert this coefficients and take and write basically the rest between the states n and m, right? So like this. So I put everything that doesn't depend on the coefficient n between these states n. Okay, so now we can notice that the expression in the parentheses is actually a product of two operators. The first operator is our observable operator A here. And we can introduce another operator highlighted here. And this is actually, this is exactly what we mean by the density operator, right? So I highlighted this formula, the definition for the density operator. I mean, putting this formula into a frame. Yeah, so as you can see, this density operator takes into account both the classical uncertainty and quantum uncertainty. And of course, if you know everything about the system, or if you have just one subsystem, one particle in my system, then I have only one p, which is equal to 1, because I know everything about the system. And then the density operator simplifies to just this outer product of psi states. Otherwise, if we know, or if we have this classical uncertainty, classical probability distribution, we need to write the formula, this density operator in this way. Of course, if we deal with the continuous spectrum, right? So the spectrum can be continuous. And if you deal with continuous spectrum, this formula can be rewritten as an integral over the density, the distribution density. So we introduce this formula to the expression above. Okay, so it's gonna be, and recall that this is actually the expectation value for the value A, or for the operator A. I probably should write A operator here. Right, so this expectation value for the operator A now is given by this summation like this. Right, so I simply rewrote this expression here, just introducing the definition for the density operator. Okay, so it's an expression like this. So now I know that the product of two operators is just another operator, right? And I can represent this operator in a matrix form. And writing this expression like here is nothing but taking the diagonal components, because these coefficients are the same, right? So it's taking the diagonal components of this operator rho A. And summation over the all diagonal components is simply, I mean, it's denoted by the trace. So the trace of an operator is some summation of all diagonal elements of the operator. And so we came to a very simple yet very important formula. I would say one of the most important in quantum theory, which says that in order to obtain the expectation value for any operator that represents physical observable, we need only take the trace of the product of this operator with the density operator. Okay, so this formula written in this form can be used in mixed state, but also it works perfectly well in the pure state as well. So you just use the density operator in a pure state, and you can use the same formula for the pure state description. Okay, so let us discuss a few properties of density operator rho. So first of all, density operator is Hermitian, and it's easy to see because when I dagger the density operator, right? So I dagger this density operator in a explicit form written between the parentheses. The classical probabilities or probabilities, they are real values, so the dagger doesn't affect. And the dagger of this outer product of two vectors, of the same vectors, is produce the same thing, because dagger, I remind you, dagger of the product of two vectors is the two vectors dagger written in the reversed way, right? So taking the dagger of this expression here, instead of cat bra, I get bra cat, but then taking the dagger, it returns me the same expression. So, which is basically the same formula for the density operator. So the density operator is always Hermitian. Another property that also, general, is that the trace of the density operator itself is 1, provided that all states are normalized. So we don't. Let me clarify this. So these are different states of quantum system. We assume that they are normalized, so the norm of this vector is 1. However, we don't require that the vectors are orthogonal, so they can be I mean, they can be not orthogonal. In fact, usually the mixed states, they are represented by not orthogonal vectors. Yet, if we take this formula for the density operator and multiply this operator by the basis vector is unitary and normalized and orthogonal. Okay, so if we multiply this density operator from both sides by vector n, the basis vector n, so we come to this expression here. Then taking the trace of an operator means that I sum up this quantity for all possible n. Right, so I sum up this one for all n. This is the result. And next, again, these two inner products are complex numbers, and I can write them in a different order. So I can, for example, put this number before the first one, like, and the result is here. And then I notice that summation over n of these two vectors in the middle is the identity operator. And the identity operator, so I omit this identity operator. The result is here. And now we use this assumption or requirement that the psi vectors are, they have norm 1. Okay, so we simply come to this conclusion, and the classical probability, of course, also normalized. So some summation up all these classical probabilities give us 1. So the trace of density operator is equal to 1. And that's fair for any density operator, for any mixed or pure state. So now I bring this property that is fair for only pure states. Okay, for the pure states. So if I square the density operator, the result is density operator itself. That's very easy to see. So for the pure state, we have only one term like this. Okay, and then I just square this operator, which means I take the operator twice, once, twice, and then I notice, and then I recall that my psi state is normalized. So this quantity here is 1, and the result again is just density operator itself. So again, this true only for the pure state. And let's say in some problem, one asks you to define if the given density operator represents a pure state. So you just take the square of the density operator, and if result is the density operator itself, then the system is pure in the pure state and represented by the density operator like this. And finally, another criteria for density operator in a pure versus mixed state is this one. So in a pure state, the trace of the square of density operator is 1. Again, it can be easily shown in a similar way. However, in the mixed state, the trace of the square of density operator is always less than 1. So again, this criteria can be used. Let me actually highlight this one, because this is quite important. This is quite important because this is the criteria that allows you to define whether your system in pure or in the mixed state. So having said all this, let me give you this example, simple yet very important, specifically for the rest of the course. So let us consider the density matrix of a qubit in a pure state. Okay, so a general state of a qubit is given by this combination, the superposition like this, where the zero state is column 1, 0, the state 1 is column 0, 1. The density operator in the most general form is written here. For the pure state, we have only one term here, this one. Then we substitute for the Bryan-Cat vectors the following most general states of a qubit in this formula. And then after simplifying and some algebra, we get expression like this, which is written in the outer product representation. So now, recalling the matrices for these outer products we discussed maybe last week. So this is basically nothing but the matrix 1, 0, 0, 0. This is the matrix 0, 1, 0, 0, and so on. So we can represent this expression in a matrix form written here, right? And recalling that these two quantities is the absolute value squared of the complex value C0 and C1. So we get this matrix like this. So this matrix is the density operator of a qubit in a pure state. Pure state, in this case, as well as in other states, means that the qubit doesn't interact with the rest of the world, with the environment, so it doesn't lose the energy. So it's a conservative system, and we know everything about the system. Okay, so since we know everything about this qubit, except for the intrinsic quantum probability, we can describe the system, this qubit, using this density operator matrix. And a few words about the coefficients. So coefficient 1, 1 and coefficient 2, 2. These are probabilities of finding system in the state 0 or the state 1, respectively. And the off-diagonal components, C sub 0, C sub 1, they provide the quantum interference. Okay, so they provide basically the energy as state exchange between the state 0 and state 1. So state 0, state 1, they coupled, and the coupling strength between the states is provided by these quantities here. Okay. All right, so the point we started with is the vast majority of quantum systems, they are in the mixed state, simply because we always have some level of classical uncertainty about the system. Like if we describe a quantum computer, of course, it interacts with the rest of the world, and we cannot describe this interaction, so we have to use this density matrix approach. And the result of the interaction of a quantum system with the rest of the world leads to two very important effects, summarized here. So let us, for example, consider a qubit again, and we assume that the qubit is excited by some stimuli, It can be, for example, an optical pulse or electromagnetic pulse. So we can excite the system, for example, from the state 0 to the state 1, if this 0 and 1 represent states with different energy. Right? So then, after a while, the experiment says that after a while, namely after some time we denote by T capital 1, the system relaxes to the ground state, to the lower states. Okay, so this process is known as the relaxation or decay, decay process. So this is one important effect here. Another effect is so-called dephasing. So let us consider the system right after excitation. So we excited the system jumps to the excited state. For example, electron transit to the state 1. However, in this excited state, the electron don't just reside in this like energy level. It also oscillates, and this oscillation preserves the phase of the excitation that we use to basically excite the atom or qubit to the upper state. However, this oscillation decays with the characteristic time t star 2. So this t2 star time is known as dephasing time, and the process is known as dephasing. So the system loses the phase of the excitation stimuli. Dephasing always contributes to the relaxation. So the relaxation, vice versa, actually. The relaxation always contributes to dephasing. So dephasing time, poor dephasing time, denoted by this star here, is always less than relaxation time. And if you take into account this poor dephasing and relaxation, we can write the formula for the actual relaxation that takes into account both for the actual dephasing, which takes into account both relaxation and poor dephasing. So here is the formula. As you can see, this total relaxation time depends on the decay time and dephasing time. So as a result of dephasing, the quantum system, the quantum state of the system of consideration is given by this exponentially decaying factor. Okay, so the way how we introduce the dephasing in the system, we multiply the state vector by the corresponding exponential factor that takes into account the dephasing. All right, so yeah, after this total dephasing time, the quantum coherence of a quantum system is assumed to be lost, right? So for quantum systems like a quantum computer, we need to, this T2 factor 2 time is very important. So we need a system with as large as possible dephasing time. So if dephasing time is large, the system preserves the quantum state for a long time. Okay, and this dephasing time basically limits all the quantum operations, quantum algorithms. It limits all the classical, all the quantum effects that we hope to use in quantum computer. So we need systems with very long dephasing time. Okay, what are typical T1 and T2 quantities for the modern quantum computers? So it's a nice point to get you familiar with this IBM quantum experience. And I encourage you to get yourself, get an account in this IBM quantum system, because we will use this one for actual quantum simulations. So in order to create, you just click here, create an IBM ID, right? I already have one. And having this IBM ID, I just log in to the system with my credentials. And get to the IBM quantum. So here, the points of interest for us will be the IBM quantum composer. Here we will create the quantum circuits. And another one, IBM quantum lab. Here we can write quantum code algorithms using Python. Okay, so we'll discuss this in more detail as follows. For now, let us go to, I guess, simulators, all systems, and see the list of available quantum computers. Okay, so this is the list of different quantum computers, real quantum computers. So you can use some of this for quantum simulations. And let us check the parameters of this. So let's, for example, look at this Sherbrooke quantum processor. Here, so details indicates that this processor gets 127 qubits. And important, yes, the parameters here, the decay time T1 and dephasing time T2 represented here. So as you can see, this T2 is less than T1, and the characteristic typical value for this decoherence time is few hundreds of microsecond. Okay, so it's a very small number. It's a 1 millionth of 1 second. Still, if your electronic part, the hardware, is fast enough, you can do the quantum computations even with a system with such a small decoherence time. So it's not seconds or hours, it's a few hundreds of microseconds. So another example, yes, another like 200 microseconds. Another system, again, roughly 200 microseconds. Here you also can see the structure, right? This map of the quantum processor. Each circle here represents different qubit. Okay, the different qubits here, they connected. Some of them have only 2 connections with neighboring qubits. Some of them have 3 connections. Anyway, so this topology of this particular computer. Of course, the topology can be slightly different, but the idea is, is pretty much the same. The idea is to have an array of qubits and make them couple to each other in order to create the entanglement between different parts of the topology. Okay, so typical values for the relaxation and decay times, a few hundreds of microsecond for superconducting Josephson junction-based quantum computers. For other platforms, these times can be very different. For some solid-based quantum computers, these times can be seconds and even minutes. However, the hardware that is required to operate these qubits will be also like very slow. Okay, so there is a golden trade-off between the operation time and the dephasing time of any qubit. So finally, we came to the postulate number 10. This is the last one. Of course, quantum mechanics, quantum in general is very broad topic, and here I don't touch upon many important things, but I plan to discuss them in what follows. This postulate is just the most important thing that I require to know and understand for understanding the rest of the course. Okay, so this postulate is about description of a composed system. Okay, so for example, I know everything about one system, I know not everything about the second system. What if I bring these two systems together and make them interact? So how I describe the quantum state of this composed system, this composition. So the postulate tells us that the description of a composed system is done by a tensor product of individual qubit states. Okay, so we discussed tensor product in one of the first lectures. Here we're gonna make use of this concept. So the formulation of this is as follows. So suppose we have two systems. One is described by psi vector, the state vector psi, in Hilbert state H1, and another one described by, let me actually use psi 1 and psi 2. In the Hilbert state H2. So as a postulate, we say that the Hilbert space of the composed system, the system composed by the two, is given by the tensor product of two Hilbert spaces, H1, H2. Again, tensor product is given by this time, like this circle with a cross in it. And mathematically, it's just a map that generates a larger space from these two. Okay. Likewise, for the state, so for this bigger Hilbert space, we have a new state, right? And the new state is given by the tensor product of two states of the single system, representing each of the single system. This tensor product, we can write this tensor product in this explicit form, state 0, tensor state 0. However, in terms of, for the sake of to make everything more in a simple way, we can use this representation like this, just the the two states of the system, which each of these encodes the state of the particular subsystem, like this. So we basically just omit this tensor product operation. In explicit form, this is in the matrix form is given like this, and the result of this product is this vector here. Similarly, for all other free states of a system of two qubits, given here, represented here, right? So it's just 4 vectors with just 4 vectors encoding the state of each possible state of the composed system. So these 4-dimensional vectors are new basis vectors in the new Hilbert space. Okay, and again, the quantum state of the combined system can be written as a linear superposition of all these 4 vectors. Using SymPy quantum, as I said last time, we can generate the qubits, right, in the ket state. We can, of course, dagger the qubits to get the bra state or bra vector. Using the represent, we can explicitly write the states in the matrix form, like this. And what about the qubits or the systems with a larger number of qubits? It's also very simple. I just write qubit, and then in these quotes, I write the particular vector. So this qubits 0, 0 will represent the state 0, 0 here, given by this vector column 1, 0, 0, 0. Let us check that. So this is the qubit itself. I can represent this qubit in the vector form, and indeed it is state 1, 0, 0, 0. Likewise, we can generate other states. Okay. So I can generate all these 4 basis vectors of a system composed of 2 qubits. All right. What about tensor product? So tensor product also can be done using the SymPy quantum library. To do so, I just need to import tensor product from SymPy quantum. And in order to take the tensor product, I just write tensor product and then the 2 qubits divided by comma. Okay, so this is tensor 0, 1. And if I need to represent this one in the matrix form, yes, indeed, the tensor product of state 0 and 1, 0 and 1 generates this 0, 1, 0, 0, 0, 1, 0, 0 state. Yeah, as I said, we can create states of multi-qubit systems. Here is the all 4 vectors. And of course, we can go to the systems with a larger number of qubits. Let's say I have a system with 3 qubits and I'm interested in a state 0, 0, 0, for example. So it is qubit is this state, and if I represent the state in the matrix form, this is the result. And adding more, adding more qubits to the system generates a vector with a larger dimension, right? The dimension of this vector, the number of components in this vector, is given by 2 to the power of n, where n is the number of qubits. So, for example, in this case, for example, this is the system of 3 qubits, and 2 to the power of 3 is 8. So I get the vector with 8 components. Another interesting point to notice here is that all these basis states are represented by vectors with all zeros except for one unit. And the position of this unit is given by the this binary string in the decimal form. Okay, so for example, the position 1 is given by this decimal 000. Right. The state 2 is given by 001. So it's located, this unit located at the position 2. Then the state 3 is given by 010. The next one is 011, and so on. So all these states represent a vector with all smaller, with all zeros except for just one unit somewhere. And the position of this unit is given by this digital string of zeros and ones in the decimal decimal form. It should be pretty clear. All right, so let us consider 2 qubits in a most general state, psi1 in the state A and B, and psi2 in the state C and D, right? And take the product, the tensor product of the two. So here is the result. So as a result, again, we get the vector of 2 with 4 components, AC, AD, BC, BD. And writing down this vector in the basis form, we get this result, right? AC and then state 0, 0, AD plus state 0, 1, and so on. And these coefficients A and C, just complex numbers, we can multiply them and represent them by these coefficients C sub 0, C sub 0, 1, C10, C11. Right, so we got 4 terms in this superposition. In general, as I said, if we have a system of n qubits, the state which represents the state vector which represents the state of this n qubit system will contain n terms. Oops, sorry, 2 to the power of n terms. And the corresponding matrices, the operators will be also matrices with 2 to the power of n by 2 to the power of n elements. So these dimensions of the vectors and matrices, they grow exponentially with the number of qubits. Adding 1 qubit to the system doubles the number of terms and doubles the rank of the matrix that represents these states. Yes. So let us now look at this expression here. So this expression has been obtained by tensor product of states of two subsystems, C1, C2. And likewise, I can basically rewrite this expression back as a product of two states. However, one can ask, what if I get, for example, these two terms 0? Okay, so I don't have them. In this case, the state will be non-separable, because in this case, I will get the state like this: state 0, 0 plus state 1, 1. Or equivalently written in tensor form like this: 0 tensor 0 plus 1 tensor 1. Important difference between this state and this state above is that this one is not separable. I cannot write this state as a product of two states of different systems. It's not separable state. And such a non-separable state is known as the entangled state. So, do such states exist in reality? The answer is yes. And today we can relatively easily generate these states. And yeah, so this is how nature works. So when you bring two quantum systems together and prepare the resulting system in an entangled state like this, the system becomes, well, entangled. And that means that if you do something, if you measure one part of the system, it inevitably leads to the change of the state of the second system, of the second subsystem. This is in drastic contrast to states like this: state 0, 1 plus 1, 1. Right? These states now can be written as a product of state 0 plus 1 times state 1. So this is separable state, in contrast to non-separable state written above. Important case of a non-separable entangled state is so-called Bell states. There are 4 Bell states, all written here. Okay, I framed the first one because this is maybe the most important one, but all of them represent different states which are totally entangled. Totally entangled states. You can check that you cannot write these expressions as the product of two states of two systems. Bell states, we're gonna use them quite intensively in this course. And last note about the operators. So when we combine the systems together, what happens to their operators? Well, the operators, we also take the tensor product of the operators. The operators will be represented by the matrices 4 by 4. And yeah, so let's say operator A acts on the subsystem A and operator B acts on the subsystem B. Then this tensor product will work like this. So it's always, if before interaction, the operator A acts on the subsystem A, it will still act on the subsystem A. All right, and a few words about quantum parallelism, finally. So, as we discussed, if you have a system of n qubits, it is represented by states with 2 to the power of n components, acting in a Hilbert space of 2 to the power of n dimensions. So how large this number can be? So modern quantum computers, they have a number of qubits around 500. In fact, recently IBM announced a quantum computer with a number of qubits of 1,000. So this number can be quite large. Still, it's not sufficient for the most of important applications, but yet, if you take this, if you calculate this 2 to the power of 500, I did it here. So if you just take 2 to the power of 500, it will be a very large number. So I represented in this exponential form. So the number is huge. The result is 10 to the power of 150. So this number is much, much larger than the number of particles in the universe. Okay. Still, today we can combine 500 qubits in a computer and encode such large number of components of terms of vectors that represents a particular state of a quantum system. This is known as quantum parallelism. Because you take, so let's say you start from 500 qubits. The 500 qubits can encode the decimal digit string of 500 elements long. So it's a relatively short number. But then you encode these qubits, or you encode a quantum state in these qubits, and this quantum state will be represented by 10 to the power of 150 components, right? So you expanded the number of quantities in your system by this colossal number. Then you do something with these components using the quantum gates. We will discuss them in the next lecture. And then you conduct the measurement. And the measurement returns all the qubits back to the basically digital string of 500 digits long. So this is the concept of quantum parallelism. You parallel a lot of quantum components and do computations with all of them in the same time, simultaneously. And here, yeah, and here I basically want to once again emphasize that having a qubit in this state 0, 1, 0, for example, is nothing but having 1 in the vector column of zeros with just 1 unit here at the state, at the place 5. And using the integer qubit representation, I can like this. So the qubit 5. So this is the qubit in the integer representation. Like say qubit 10. Qubit 10. It's just it's not qubit with 2 states 1 and 10. It's a qubit with it's a system of 10 qubits represented by some. Anyway, so this is the end of the lecture number 6. Let me stop the recording and thank you for your attention.